Hey guys, this video we want to conquer D-type flip-flops. So let's dive in. For the purpose of context, I'm going to want to go through some things that you may not need to know in detail for the OCR A-Level specification. But I will include some information to help you get a better understanding, so you've got some more context. The things you need to revise will be in Greek outlined slides. So previously, we've spoken about the fact that logic gates can be used to automate decisions based on inputs passed through particular transistors, in other words, logic gates. Logic gates can also be used to store data. We focus particularly on AND or NOT gates. We haven't looked too much at XOR gates, but we will when we approach encryption in another video. So another gate we're going to look at is the NAND gate. The NAND gate is a combination of the AND and NOT gate, essentially flipping the result of the AND gate. The circle at the end of the AND gate represents the NOT gate. This can also be done with an OR gate to produce a NOR gate. This is something that is not really covered in the exam spec. Although they're not really required, it is useful to understand what the NAND gate is. This is what's known as a D-type flip-flop. As mentioned before, as well as using gates for decision making, using an array like this, we can also store one bit of data. This uses the principles of De Morgan's first law that not A and B is equal to not A or not B. This is probably a topic beyond what's required for the A-level spec, so I won't delve in too much into this, but I'll briefly try to explain how the array of NAND gates that makes the D-type flip-flop is used to store data. To be fair, knowing how the D-type flip-flop works is also not that important, but as you'll see in a bit, it may be important for context. The array of NAND gates uses what's known as a set-reset latch. If both the set and the reset are kept high, or in other words 1, this means that the output of the set NAND is a 0. This is then fed into the reset NAND. Let's mark that here. As a 0, the output is then flipped into a 1, as you can see here. This would result in an output of Q equals 0. This is now our stored bit. If the set switch is changed to 0, the result of the set NAND is changed to 1. And this is fed into the reset NAND. Now the result of Q is 1. Now something that is very important to know is that the motherboard has a clock speed that is very important to help all the other components of the computer run in sync. So the CPU clock speed is determined by multiplying the motherboard or the system clock speed. You don't need to know this for your exams, but you may have heard of people overclocking their CPUs to run faster. Generally, this is done by incrementing the master clock speed. If the CPU clock speeds are increased, they wouldn't be in sync with the rest of the system. So if the motherboard clock speed was 100 MHz and the CPU clock speed is 24 times this, the CPU clock speed would be 2.4 GHz. So if we make a slight change, if the motherboard clock speed was 100 MHz and the CPU clock speed was multiplied by 45, then this would mean our CPU clock speed is 4.5 GHz. Now, this is where it all ties together. And I did mention before that our green slides are the ones that you really need to know. The rest are for context, right? So the system clock speed is used in a D-type flip-flop as our reset input. So you can see here I've labeled it as C. We refer to the set as D since this is our data input. So this is a visualization of the clock running at a constant speed, providing a pulse that we can use to set Q if we set our data input at the right time. And by the right time, I mean that Q can only be set if D corresponds to the clock's rising edge. We can see here that the clock has a rising edge, which we've labeled in blue. So if we're to pass data as either 0 or 1 through our D-type flip-flop array, the value of the output is held until the clock sees the value at its rising edge. This is known as an edge-triggered D-type flip-flop. So here we can see that Q only changes after the rising edge of the clock pulse, even though D may have changed earlier. So here we can see that D changes to 1, and that happens at the same time or even just before the clock, and as a result Q changes to 1. Then we can see that D changes to 0, but because this has happened before the rising edge, Q doesn't change yet until it reaches the rising edge of the clock, and at that point then Q is changed to 1. Then when D changes to 1 again here, Q doesn't change until the rising edge clock, in which case the output is changed for Q. In this example, we can see that the value of D changes a few times, but does not affect the output of Q unless the changes correspond to a high pulse of the clock. We can see that here, where Q doesn't change until after the rising edge of the clock, where Q is affected. So in the exam, you're not really required to remember how to draw a D-type flip-flop. The NAND gates are not actually referenced in the exam spec. Only the concept of a D-type flip-flop. Most of what I've demonstrated has been for context. Instead, you'll see a diagram like the one to the right. So in summary, the points you need to remember are that D-type flip-flops are circuits which use logic gates to hold the value of 1 bit. These values can change based on signals, as we've seen. There are 2 inputs, which are D, which is our data, and C, which is the clock. And the 2 outputs we have are Q and the opposite of Q. When the clock input pulses at high, Q changes to the value of D. So with that in mind, as always guys, please check out the link to the website. We have some exam type questions for you guys to try out and practice. And I'll see you in the next video.